Hey friends, today we will see economical load scheduling coordination equation or optimal operation condition without transmission losses. But in order to share the load within economical manner, what is the coordination equation? That equation we have to determine whenever the transmission losses are not considered. Whenever the transmission losses are neglected, what is the optimal condition equation or coordination equation for economical load distribution? So for that, first let us consider small n number of generating plants. N number of generating plants are interconnected in a system. Each and every plant is generating some power. Those with generations Pg1, Pg2, Pg3, dash dash Pgn respectively. That is nothing but first plant generating Pg1 power, second Pg2 power, like that up to nth plant is generating Pgn power. So each and every plant, in order to generate the power, certain amount of the cost is used. Those costs are, for the first plant, in order to generate the Pg1, they are spending on money. In order to generate the Pg2, we are spending C2 cost. In order to generate the Pgn, we are using Cn cost. So why I consider the cost is nothing but here our intention is optimal condition, optimal coordination equation, economical load distribution. But we have to shape the load within a less cost manner, within a less cost of generation. That the main objective function here is to be cost function. Okay. Now here the total cost, individual cost equations are C1, C2 up to Cn. Then can write total cost equation. Cost total cost equation is C equal to C1 of Pg1 plus C2 of Pg2 plus dash 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 plus Cn of Pgn. Now finally here I am calculating the total cost equation. Now this equation is modified as individually I written as single equation, that is total cost equation C equal to summation I equal to 1 to n ci ci of Pgi. This equation number you have to consider as first equation. Now this is the main objective function, that is the minimization of a cost function. That is the main objective function here is to be minimization of cost function. You have to consider the first equation. Now how we have to minimize this cost? How we have to minimize this cost is but by satisfying the equality constraint. Let us consider next. Let us consider. Let us consider. Let's consider equality constraint. Equality constraint. But we have to share the load within economical manner by satisfying the equality constraint. So what is the equality constraint? Is power generation. Power generation, that is total power generation Pg terms of Pg is equal to power demand. Power demand. But here this equation is according to right. What is the total power generation? We consider here small n number of power plants. So what is the total power generation? Becomes Pg1 plus Pg2 plus dash 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 plus Pg equal to power demand P. Now this total power generation is written as equation summation I equal to 1 to n Pgi or not. Same equation written in terms of summation is equal to power demand. Now this here I am changing this equation as summation I equal to 1 to n Pgi minus Pd equal to 0. Now you have to consider this is second equation. This is second equation. Now in order to obtain the optimal condition or coordination equation, we have to find out the condition. But how we have to solve the above equation? Nothing but above two equations are nonlinear equations. Those two equations we can solve by using one function, that is to be Lagrange equation. The above cost equations are nonlinear equations. So now finally this we can solve by using Lagrange method. Now the problem can be solved. The problem can be solved by the method of by the method of by the method of Lagrange Lagrange multipliers method. Lagrange multipliers. Lagrange. The problem can be solved by the method of Lagrange. Now, how we have first we have to evaluate the Lagrange multiplier equation. Now, after evaluating the Lagrange multiplier equation, then you can find the final optimal condition equation. Now, what is the Lagrange equation is nothing but now how we have to write the Lagrange equation is here. Lagrange equation, how we have to write the Lagrange equation, that we can represent L, capital L equal to first write objective function objective function objective function minus lambda into constraint equation. Constraint. Now here substitute objective function and constraint equation. Finally we get the Lagrange equation. Now here what is objective function is nothing but our intention main objective function is we have to reduce the cost function. This is the minimization of cost function. This cost we have to minimize. This is objective function. This is objective function. Now here write the objective function, that is summation I equal to 1 to n ci of pgi minus lambda into constant equation, that is the second equation. That is second equation is summation I equal to 1 to n pgi minus pd, the constant equation. Now this is the Lagrangian equation. This is the Lagrangian equation. This Lagrangian equation we have to solve and then find the optimal condition, that is the minimization equation. Okay. Now here what is lambda is nothing but lambda is the Lagrange multiplier. Lambda is a Lagrange multiplier. Lagrange multiplier. Now finally we have to find out the minimization of the function, minimization of Lagrange equation. The minimization is achieved by the condition. That condition is derive the Lagrangian equation with respect to power generation and equal to 0, because here power generation is the variable, that's why you have to differentiate the equation with respect to power generation. Now minimization is achieved by the condition that condition is derive the Lagrangian equation with respect to Pgi and equal to 0. Finally we get the optimal equation. Now derive the third equation with respect to generation. So how we have to derive the third equation? Please everyone listen carefully. So in third equation, in Lagrangian equations, how many terms we are having? Total we are having the indirectly 3 terms. Total we are having 3 terms. That is, this is the first term. This is the first term. This lambda into summation I equal to 1 to n into pgi is we can as the second term. Lambda into PD you can consider as a third. Okay. Now, how we have to derive this one? First, we are deriving the first. That is, derive the summation I equal 1 to n Ci of Pgi. So actually, this Ci of Pgi is nothing but not a constant value. Yes, Ci of Pgi is nothing but cost equation. That is cost equation Ai Pgi square plus Bi Pgi less Ci. So if you know the equations Ay value, for example, this first plant will get the A1, B1, C1. If you know these values, then finally you can derive directly. That is derivative of Ci of Pgi. According to that, we have to derive the equation. But here, this is unknown equation. This is to be one equation. After they will give the equation, you have to derive that equation. But present that unknown equation. That's why this first term you have to write as it is in terms of derivative only. In terms of derivative only. After knowing the equation, you can derive. So first term you have to derive as it is in terms of derivative terms only. That is the derivative of Ci of Pgi by dpgi. Same as it is in terms of derivative of right. Don't derive at this condition because that is unknown equation. If you know the equation, you can derive something, any value, that is to be 3 p1 square plus 4 p1 plus 20. Now we can derive, no problem. But it is unknown equation, so but right in terms of derivative term b. Next, minus lambda into second term. Second term is summation I equal 1 to n pgi. So that is pg1 plus pg2 plus pg3 dash 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 pgn. So here we are deriving this is with respect to power generation pg1 or pg2 or pg3 only. So if it is pg1, we are deriving with respect to pg1. Whole pg1 becomes 1, remaining all terms 0, because this pgi is pg1 plus pg2 plus pg3 equal to pgn. For example, you are deriving this equation with respect to Pg1. Then finally we'll get the equation. This is only first term becomes 1. Remaining all terms are 0. That's just 0. That is power generation. We are deriving the dPg1 by dPg1 first. If it is second one, dPg2 by dPg2. That is 0 plus 1. So like that, we'll get here it is 1. Here we are deriving the PGI with respect to PGI. dVL by dPGI. PGI with respect to PGI will get the 1 minus PD. PD is a demand value. It's not a generation value. But we are deriving this equation with respect to generation value. So that this PD you can conclude that it is to be constant value. So the derivative of constant becomes 0 equal to that you have to make it as 0. And the dl by dgi equal to. So based on this condition, now simplify this equation. That is dci of pgi by dpgi minus lambda into 1 minus 0 1. So minus lambda. You can shift to right hand side to find the lambda. So finally dci by dpgi by dpgi is required. It is to be optimal condition for I equal to 1 comma 2 comma dash 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 n. Now this is to be optimal condition equation. This optimal condition equation you can write as also this is coordination equation. Coordination equation or optimal condition. Optimal operation. Optimal operation. Or operation condition. Optimal operation condition. Now here this is, you can simplify. If it is I equal to 1, you get the dc1 of by 1 equal to dc2 by d by dpg dash 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 dcn of n by dpgn equal to now this is sorry, So same equation I written for I equal to 1 and I substitute. Now finally we can think that these are the coordination equation. Now this is to be what is we can call it as the incremental fuel cost. The incremental fuel cost of all the plants are to be same. This is nothing but optimal loading condition. The optimal loading of generator corresponds to the equal incremental cost point of all the generators. So finally, this is to be coordination equation or optimal operation. Here lambda is nothing but that is Lagrange multiplier is equal to fuel cost equation. Now this equation also we can write as this we can consider incremental fuel cost equation. So IFC 1 equal to incremental fuel cost of second plant equal to dash equal to incremental fuel cost of nth plant is equal to lambda. Incremental fuel cost of all the plants are is to be coordination equation or optimal operation condition equation whenever the transmission losses are negated. Friends, this is related to optimal operation condition. Simply once again you have to see overview. First consider the n number of lines. According to that, consider first total cost equation, that is first equation. Next consider the equality constraint, power generation equal to power demand, that is second equation, summation equal 1 to n PGI minus PD equal to 0. So these first and second equations are nonlinear equations. We can solve this equation by using Lagrange multiplier method. So Lagrange multiplier method, you write the equation L equal to objective function minus lambda into constraint equation. So here objective function is summation equal 1 to n Ci of PGI minus lambda summation equal 1 to n PGI minus a. This is Lagrange multiplier. Lambda is nothing but Lagrange. Now minimization is achieved by the condition derivative of Lagrangian equation with respect to power generation PGI and equal to 0. Then by doing like this we will get the dCi of PGI by dPij equal to lambda. Here I equal to 1 to up to n. Now finally this is nothing but coordination equation or optimal operation condition. Now by equating all the terms we will get the lambda, that is IFC1 equal to IFC2 equal to IFCn equal to lambda. Okay, thank you friends. If you like the video, please subscribe my channel and share the video to your friends. Thank you friends. Thank you.